started off with separately excited DC motor. So we looked at actually separately excited DC motor, which we said is very much similar to a PM DC motor, that is a permanent magnet DC motor. Only thing is there is no scope for change in excitation, whereas this will allow IF to be changed as per whatever is the voltage that I am applying, but normally the voltage I apply will be the same as that of armature voltage, because most of the times only one single DC voltage may be available as a supply voltage. So I may have this as the armature, and I am going to have this as the field, and I may have a resistance in series. For some reason, if I want to reduce the field excitation to the motor. So this is going to be a variable resistance. Let me call this as R external. The resistance of this is RF. This is VF, which should be hopefully same as VA. So this is the armature voltage, and we are going to have a shaft which is connected to this, to which the load is, here is the load. So I am going to have a mechanical load which is actually rotating at a speed of omega because of the motion that was, or the torque that was imparted by the motor to the shaft, and hence to the load system as well. So I am going to have TE equal to K phi omega. I may call this as KE phi omega. So I can write this as some K into IF multiplied by omega, where IF is going to be VF divided by RF plus R external if I am having an external resistance also connected in the field circuit. And I should also be able to write that there should be a back EMF induced here with plus here and minus here, and the current that is flowing is IA, and the armature resistance here is RA, because of which I am going to have VA minus IA RA will be equal to EB, which is the back EMF, which incidentally tells me when I start the machine, right? If I am starting the machine, at that point I am going to have omega equal to 0, the speed is 0, right? So if I look at this equation, I can right away say at starting I am going to have omega equal to 0. So EB will also be 0. So I am going to have VA minus IA RA equal to 0 during starting, which clearly tells me that if I try to look at what is IA, it is going to be VA divided by RA. Torque is not a function of omega. Torque is TE equal to, sorry, K phi IA. I have written this and then none of you guys told me. This is IA, clearly, K IF IA. Back EMF is a function of omega. Sorry, KE phi omega. Sorry. So this is essentially a function of armature current, clearly. No relationship directly between the speed and torque like this. We'll have to look at the relationship which we already looked at. So this is going to be, if I just take for a normal 2.2 kilowatt motor or something, this may be of the order of 1 ohm. Maybe this is 220 volts. So this is going to be 220 ampere. Whereas the rated current may be of the order of 10 or 12 amperes, nothing more than that. So I'm going to see that a very, very huge current flows through the armature circuit if I don't include any external resistance during the starting condition of a DC motor. So it is very essential to have a starter. So this necessitates employing a starter. So So unless I employ a starter, and starter is by and large, in most of the cases, it will only have a large resistance, nothing else. Starter will generally consist of a very large value of resistance. So if I have a large resistance included in series here, so I may call this as the starter resistance or starter rheostat, because it will be a variable resistance. So I'm going to have a starter rheostat. This starter rheostat will be included in such a way that the maximum resistance is included, which would be actually limiting the armature current well within the limit that can be tolerated by the commutator and armature conductors. Most of the times when we design machines, we'll give a factor of safety of 2 or 1.5, 1.75, depending upon what kind of requirement I have. For example, if I am talking about an elevator will definitely have a requirement for a very high starting torque, because many of us would get in and after that only the motor is going to start. You can't say I'll start the motor, you jump in after that. That's not possible. So you have to have a large starting torque requirement in certain applications, like for example an elevator, a train. A train will have multiple number of the cars attached, right? Bogies attached to the engine. So all of them have to be essentially pulled. If all of them need to be pulled, you require a huge amount of starting torque. So if I require a larger starting torque, very clearly as the torque equation indicates, I will require a larger armature current as well. So I may put the limit on the armature current as twice the rated current or something like that, the peak current that can be carried by the armature, not on a continuous basis, for a short while. For a short while, I may allow my machine to carry twice the rated armature current. So if I actually put a limit like that, then I'm going to include an external resistance. So I would say VA divided by RA plus R external should be less than maybe 2 times IA rated. I may put a limit like this. So I would choose my external resistance value or the starter resistance value in such a way that the current is limited to 2 times the rated current. I am just giving an example. It can be 1.75, it can be 1.5, depending upon what kind of requirement I have with respect to my motor. For example, if it is a fan which is being driven by a DC motor. For a fan which is very similar to a windage loss, I had told you for windage generally torque is going to be proportional to omega square. This is for windage, which is actually showing how much is the resistance offered by the surrounding air. So if I have a load which is like an elevator, if I have a load like a train, or if I have a load like a fan, the characteristics would be very different in terms of load, speed, torque characteristics. So I am going to have requirement of different values of torques for different situations, according to which I will say my machine can carry a maximum of so much of torque or so much of current and so on, right? Okay, so coming back to what we said actually as the EMF equation, which is VA equal to EB plus IARA, we can write EB, which is K phi omega, will be equal to VA minus IARA. Because of which I can write omega equal to VA divided by K phi minus IARA divided by K phi. But I also know that after all TE or the electromagnetic torque is K phi IA. So I should be able to write this as VA by K phi minus TE divided by K phi whole square multiplied by RA. So we are substituting the expression for TE indirectly, and then we are just replacing IA by TE divided by K phi. That's what we have done. So this clearly gives me a straight line torque speed relationship, provided I do not consider armature reaction. I have not looked at armature reaction in this particular case. So if I don't consider armature reaction, I am going to have basically, if I just say this is omega and this is torque. When the torque is 0, right? When TE is 0, omega equal to VA by K phi. Very clearly, the armature applied voltage plays a very vital role in deciding what is the speed at 0 torque or no load condition. So this is no load condition. So under no load condition, I am going to have the speed as VA by K phi. So you are going to have this as VA by K phi, which corresponds to torque equal to 0. So if I assume that I don't have any drop in the speed at all, if it is an ideal motor. In an ideal motor, whatever be the load that I am putting, I should not get any drop in the speed. But if it had been an ideal motor, I would have gotten the speed somewhat like this. But it is not an ideal motor. Clearly there is an armature resistance which is going to take a toll on the overall speed, because of which I am going to have a drop in the speed. So as I load it more and more, I am going to have a drop in the speed, and this actually is in one sense similar to IARA drop. Only thing is I can write this as a function of TE, because IA and TE are directly related, right? This is very clearly for a given, so this relationship I should say is for a given VA, RA and flux. I don't want to change the flux, it's a separately excited machine. I'm going to keep the flux as a constant. I don't want to change the armature resistance, it is inherently whatever is available. I'm not really changing that, and I'm giving rated voltage. So this is going to be the characteristics as far as the speed torque characteristics are concerned for a separately excited machine. So also will be the case for a permanent magnet DC machine. Because permanent magnet DC machine, again flux will be a constant. I'll not be able to change the flux. So it is exactly behaving in the same manner as that of a separately excited DC machine, right? On the other hand, if I look at a shunt motor, yes, that is IARA loss, but I am rather depicting this as TE divided by K phi whole square. So it is actually IA by K phi further. Which armature loss? IARA is the armature loss, armature voltage drop. So we are essentially considering the same thing. Yeah? Armature reaction I am neglecting. Currently armature reaction I am neglecting. If we are considering armature reaction, clearly the characteristic will be non-linear. It can't be linear because the saturation will get into picture. Non-linearity will definitely creep in. So we have not considered armature reaction. So I should say very clearly one more thing is armature reaction is neglected. I have not considered that at all. Armature reaction is neglected, right? So if I am considering a shunt motor, because separately excited motor and shunt motor are almost similar in terms of their behavior, right? Unlike the generator, because in the case of generator, I am not giving any supply to normally my generator at all if it is a self-excited generator. It is going to generate everything from scratch. Whereas here, what I am going to do is, here is my armature and here is the field. And probably I will include a resistance in series if I want to adjust the field. So let me call this as R external and this is RF. And this R external can be set to 0 if I want to include minimum amount of resistance, right? So along with this, I'm going to now apply a voltage which I may call that as V, because I can't call it as VF or VA, I'm calling that as V. Okay? Sometimes some of the books gives this as V terminal, VT. Right? So VT I am applying. And if I assume that again I have set this at minimum resistance value. With this as minimum resistance value, I am going to get the field current, which is actually going to be VT divided by RF if R external is set at its minimum value or R external is 0. This is what is going to be my field current. So as long as I do not change the R external value from 0, and as long as I am keeping VT same as VA, I am not really allowing that to be changed because it's a shunt machine, I am just connecting a common supply, I would say it behaves like a separately excited machine. So this is essentially going to have the same characteristics as Vt divided by K phi minus TERA divided by K phi whole square. Right? This is going to give me the same characteristics as long as I keep the R external equal to 0 and I keep the power supply Vt as a constant for the armature as well as field. So this is essentially the characteristics for shunt as well as separately excited and also for PM DC motor. So this gives me basically the characteristics for all three types of motors, that is separately excited motor, PM motor as well as shunt motor. All of them are going to have almost similar characteristics because I am assuming that I am not including any extra resistance in the field circuit. That's what I am assuming. Now, because I have this, I should be able to say at a given torque, if I want to get different values of speeds, I should be able to get different values of speeds either by adjusting the voltage or by adjusting the armature resistance or by adjusting the flux value. So three of these different methods will be employed normally for speed control of DC motors. So if you look at the speed control of, yeah? No. Back EMF is basically whatever is the reaction that you are getting as a counter EMF due to the conductors moving in a magnetic field. The conductors are moving in the magnetic field. So it is getting an induced EMF. But if you look at the armature reaction is what is actually distorted on the whole in the original flux that you had looked at the machine. So when you consider armature reaction, it's not correct to assume that the flux is a constant. Phi is not a constant anymore. Got it? The flux of the machine, which is actually produced by the field current, that will not be a constant anymore if I consider armature reaction when the armature conductors are carrying current. And in the case of motor, the armature conductors will anyway carry some current. As you load the motor more and more, I will require more electromagnetic torque, which means I will require more armature current. If there is more armature current, there will be more armature flux, there will be more amount of armature reaction. So you might see more of demagnetizing, more of cross-magnetizing, more of magnetizing fluxes. So overall flux will get distorted due to the cross-magnetization and overall flux will get depleted because of demagnetization. Because magnetization will not be able to increase it that much due to saturation. This is the major difference between armature reaction and the back EMF. The back EMF is always considered. You can never ever consider the operation of a motor without back EMF. But you can very well neglect armature reaction if you feel like what we have done right now. Yeah. That is what we said basically as the series field. The series field can be made in such a way that the series field can add or subtract. But if the armature flux itself only adds all the time, you would see ultimately completely Lenz's law being defied. Lenz's law has to exist. It cannot be defied. So otherwise the flux will literally go to infinity. It is existing in the form of back EMF, but apart from that, if you really make everywhere magnetizing, is it possible really? It is not possible, because you have to have dots somewhere, cross somewhere. What goes around comes around. You can't do anything. The current has to return. And for the current to return, you definitely have to have dots somewhere, cross somewhere. So naturally, if you have demagnetizing somewhere, you will have magnetizing somewhere, and vice versa. You can't have everything to be magnetizing. It's not possible, right? So you are not going to be possibly looking at increase in flux in most of the cases in a DC machine due to armature reaction. That is generally not possible. Yes. Windage loss, if we want to neglect, we can neglect. I have not even included the mechanical equation as yet. I have to include the mechanical equation. If you look at the mechanical equation, you have to say TE equal to TL. What you consider as the load torque is a matter of detail. If it is a fan type load, I will write TL as some C1 times omega square. If it is a constant torque load like an elevator, I will write that as simply a constant, C1 or C2. If I am looking at it as a friction, viscous friction, for example, where maybe a viscous liquid is being pumped, depending upon the velocity with which the liquid is moving, you are going to have the corresponding value of load torque demand increasing proportionately. So you will have K times omega. So you have load torque as a function of speed. It can be a function of speed square. It can be a function of it is a constant value. It can be either way. So we are essentially looking at the load torque as some value which depends upon whatever is your load mechanism. So I can have different types of load mechanism. What you have to understand is, just like how you write F equal to ma in the linear system, I should be able to write J d omega by dt equal to whatever is the torque available for accelerating it. What is the torque available for accelerating it will be what is generated as an electromagnetic torque by my motor and what is the load torque demand. When I start a motor, that's why I said if it is an elevator and let us say 5 of us get in, the electromagnetic torque demand, the load torque demand is fixed depending upon how many of us have gotten. But the electromagnetic torque has to be slightly higher than that. Otherwise, I'm not going to be able to get an acceleration. I want this to be positive. If this has to be positive, necessarily TE has to be greater than TL. Can't help it. For example, 5 of us get in, the demand is 10 Newton meter. Then you have to generate in the motor at least 11 Newton meter, 12 Newton meters. Only then it is going to give an acceleration. Otherwise, there is no way the motor will accelerate. Right? So, we are looking at, first of all, only the electrical phenomena. All these are definitely involved mechanical phenomena, what we are looking at. So, mechanical equations govern the acceleration rate, and the acceleration rate also depends upon TE, and TE is governed by armature current. So we have a link between the electrical quantity and the mechanical quantity in the form of the electromechanical energy conversion. So the current is being converted into torque in a motor. The same way in the generator, you see the same way from the mechanical power, you are converting it to electrical power. Right? So, if we are actually looking at the speed control, let me write this equation once again. I am having V divided by K phi. It may be VA or VT, doesn't matter, minus T divided by K phi whole square multiplied by RA equal to omega. This is what we wrote as the speed torque equation. Right? Now, if I am keeping VA as a constant, I am keeping flux as a constant, I am only modifying RA. If I am increasing the armature resistance by including some external resistance, I am going to have more and more drop in the form of IA-RA drop. Because of which, if I actually look at the speed torque characteristics, if this is my speed and this is the torque, I am going to have probably under normal condition without any external resistance being included, it is falling maybe slightly. So maybe it was at 1500 RPM or something. From that it may fall to 1400 or 1300 RPM. That's it. So this is ideal when RA is 0. This is with inherent RA. If I include more resistance, if I am going to include more and more armature resistance, in that case I am going to have very clearly this characteristics will steeply fall, because I am trying to actually drop a huge amount of voltage in the armature resistance itself. If you may recall, we wrote IA RA equal to VA minus EB. This is how we started the equation. So I should be able to say VA minus EB divided by RA will be equal to IA if I don't include any external resistance. Yes. I have not allowed the field current to increase. I am keeping field current fixed. I have applied a particular value of voltage to the field system. So the field resistance is fixed, 150 ohms or 200 ohms. The field current is a constant. I am not allowing the field current to increase because I am keeping basically my voltage applied as a constant. So it's not going to change. So field current is not changing. I am including increasing the armature resistance. What is going to happen to the speed? Provided I am looking at basically the torque demand. This is the torque. So maybe I am going to keep the torque demand at the same value. I can keep, if 5 of us have gotten into the elevator, it's not going to change the torque demand, whatever I do. Maybe I would like to make the mechanism move at 20 meters per second. I may like to make it move at, 1 meter per second. Depending upon my whims and fancies, I can always adjust the speed for a given torque. So this torque demand is a constant. Let us say, what I have demanded from the load side is a constant. Under that condition, I want to see whether I will be able to achieve different values of speeds. How do I achieve different values of speeds? That can be done by including an external resistance in the armature circuit. So if I say this is RA external, I can always modify the armature current by having an RA external value. If armature current is modified, I am going to get immediately right away, I am going to definitely get more amount of drop basically in the speed. So that essentially tells me that by adjusting the armature resistance, I would be able to definitely get a speed control at a constant torque demand. But this actually is going to be extremely lossy. if I look at the whole thing, I am going to have extremely large amount of losses. Please imagine the armature current is basically tens of amperes of current. And what I am including as an external resistance is going to have again probably some amount of large value, right? It may not be as small as armature resistance, but still I will have maybe 1 ohm, 2 ohm, 10 ohms, whatever. So I'm going to have a huge amount of power dissipation taking place in this particular method of speed control. So this is essentially RA external increasing. If I increase RA external, I'm going to get more and more drop in the speed for a given torque value. If I'm looking at a given torque value, I will have, drop in the speed. Please realize also that TE times omega is going to be the power output. What I am giving is VA times IA, roughly. I should not say just IA, it should be IA plus IF if it is a shunt machine. So this is going to be my input power. So obviously I am going to have reduction in the input power also probably, because of which I will have reduction in the output power, not reduction in the torque, but reduction in the speed. Reduction in the torque is not visible, but reduction in the speed, yes. I am not keeping the torque as a constant. If my mechanism asks for a constant torque value, I can't do anything, right? If I am looking at basically, that's why I gave you repeatedly elevators example. Let us say we have gotten into the elevator and all of us are just staying put there. The torque demand is a constant because it has to go against the gravity. I can make it go against the gravity at 2 meters per second, 5 meters per second. I want to change the speed. How do I change the speed? At a constant torque demand. This is what we are looking at. Right? Please understand that the torque is set in stone. It is actually demanded by the load mechanism. I don't have a control over it. What I have a control over is only the speed. See, we are looking at K phi IA, agreed. So if I am looking at basically IA decreasing, right? In all probability, when I actually look at increase in the armature current, rather increase in the resistance, my armature current should have dropped. It will drop transiently. When it is dropping, immediately what is going to happen is IA RA into R external. If I assume that is going to be now somewhat larger because R external has increased quite a bit, I am definitely going to have a reduction in the back EMF as well. So this actually will cause, not reduction, it will have an increase in the back EMF. So I am going to have actually immediately the speed will actually start dropping to bring down basically the back EMF. So what is going to happen is, if I am looking at a small reduction in the armature current, that happens transiently. The moment armature current drops, I am going to see that the back EMF might increase slightly, and the back EMF increases slightly, then you are going to see that the speed will drop to bring down the back EMF to the original value itself, so that the entire balance is maintained. If you have really a drop in the torque, then the mechanism will lose its speed because of this particular balance. This balance is lost. The load torque demand is the same, whereas the torque what I have got is smaller. So the speed has to drop. There is no other way. So it is actually a continuously self-correcting mechanism. The moment you reduce the armature resistance, you may see some oscillations in the armature current, you may see some oscillations in the back EMF. Finally, it will settle down at a value where the original torque demanded remains the same. You come back to the original torque value, but you are going to see that the speed has dropped. This is what you would see because more amount has been dropped off in the form of IA square RA plus R external drop. So more power has been lost in IA square multiplied by RA plus R external. So this armature resistance control, clearly if I am looking at VA by K phi as the no load speed or at torque equal to 0, I am going to have this as the speed. I will have clearly armature resistance control giving me the range where the speed will be less than the no load speed. Speed cannot be more than no load speed because I am subtracting it always from the no load speed. I have set VA at a constant value. So VA by K phi is set in stone. I can't do anything. If VA by K phi is set in stone, I will be only able to reduce the speed further and further. I cannot go beyond rated speed. Please remember what we have drawn as the characteristics. It is only coming below. It cannot go above. That's what I'm trying to say. It cannot go above. It has to always lie below VA by K phi. It cannot go above. Right? Let us try to take a look at another way of speed control, which is VA by K phi minus, again let me just write down the equation for the speed torque characteristic. I can definitely modify the speed by just modifying VA alone. I am looking at only one variable at a time. I am not changing everything. Everything if I change it will be more confusing. So I am looking at only one variable at a time. So if I am looking at armature voltage changed, please note that the slope of the torque speed characteristic is decided by what is the RA drop. If RA drop is more, it was becoming more steep, it was becoming steeper, otherwise it is kind of the slope is very small. So this is the normal characteristics for VA by K phi. If I am not changing the armature resistance and if I am not changing the flux, the slope should essentially remain the same. It cannot modify itself. So if I reduce the armature voltage, I will have basically parallel characteristics. So this may be for VA1, this may be for VA2, this may be for VA3, and this is essentially VA decreasing. Right? So this is TE, this is omega. When I reduce the voltage, maybe it is meant for 220 volts. I can operate it at 180 volts. If I have a rectifier, maybe I can put a auto transformer, a rectifier. I can always vary the voltage output of the auto transformer. The rectifier voltage will also change correspondingly. If the rectifier voltage changes, I should be able to get different values of speed at a given torque. So if I am talking about a given torque, this is the torque value demanded, right? So if this is the torque demanded, I should be able to get different values of speed. Maybe this is omega 1, this is omega 2, this is omega 3, this is omega 4. All of them are changing drastically because of different values of armature voltage. Yes. If it is a shunt motor, yes. That's a very good question. If it is a shunt motor, yes, it will affect flux also. So this is much more valid for a separately excited DC motor or a permanent magnet DC motor. Clearly. If it is a shunt motor and if I am using a common supply for both, then I am definitely going to have a problem with the field current as well. That will also decrease. So I should assume that maybe it is a PM motor, or at least in this particular case, the shunt winding I have to connect it to a separate power supply. Right? So I am assuming clearly here IF is a constant and RA is a constant. I am not changing them. So I am assuming for these characteristics, these two hold good. That's what I am assuming. You can vary RF, but you can only come down, right? RF is the inherent field resistance. You have RF external. You can only reduce IF. You cannot definitely go for higher values of IF because you are already operating close to saturation. Right? And inherent resistance, you can't make a negative resistance possible. That's the problem. Right? You can't really add a negative resistance. That's not possible. So, this essentially tells me actually that we are having, the armature voltage control method possible again for speeds less than rated speed, preferably. Because if I am talking about a motor rotating at 1500 RPM with a 220 volt supply normally, under normal operating conditions with rated excitation and so on and so forth. If I say that if I want to achieve a speed greater than 1500 RPM, that means I have to go for a voltage also which will be higher than this normal rated voltage. Only then I will be able to achieve a speed which is greater than the nominal rated speed. So, I have to constantly or permanently apply or continuously apply maybe 300 volts, 280 volts. Only then I am going to be able to get a speed which is higher than the normal values of speed that I operate upon with constant excitation and constant RE. But this is definitely not good for the insulation. Especially if I do it on a continuous basis, I would have basically designed my motor with the viewpoint that I don't want it to generate more than this particular value. If it is a motor, I don't want to apply more than this particular value. So the insulations of armature windings would have been designed with the rated voltage in mind. So if I try to apply a larger voltage, it's definitely not good for the machine, especially if I do it for prolonged periods of time. So generally, armature voltage control is also used. Armature voltage control is also used only for speeds less than omega rated, I would say. So whenever I am having a machine rated for say 1500 RPM, that means it will work as a motor with rated voltage, drawing rated current, delivering rated torque at rated speed. So if I say 2.2 kilowatt motor, if the rated speed is given as 1500 RPM, I should be able to calculate what is the rated torque. 2200 divided by 2 pi into 1500 by 60. I should be able to calculate what is the rated torque. So when we talk about rated speed corresponds to basically whatever is the motor delivering as the speed while it is delivering rated torque, drawing rated current from a rated supply with rated excitation. All of them under rated condition. Right? That is what is known as rated speed. So, this is the second method of speed control. So, we have seen armature resistance control and armature voltage control. Both of them are only meant for speeds which are less than either no load speed or rated speed. And you also see that the shunt motor does not have much drop in the speed. Because RA is generally small. Unless I include a very, very large external resistance, I'm not going to have much of drop in the speed. So most of the times we can say shunt motor, separately excited motor or permanent magnet motor, all of them will be fairly constant speed drives or constant speed characteristics. They have fairly, not exactly, accurately, but fairly constant speed. Because you would see that series motor is just the other way around. We'll talk about series motor eventually. But what we see in the shunt motor or PM motor or separately excited motor, right? All of them have fairly constant speed irrespective of TE delivered, right? Right? So, we are essentially looking at the shunt motor or PMDC motor as having fairly a constant value of speed, provided of course VA is a constant, flux is a constant, right? And so on and so forth. Right, and RA is also a constant. The last type of control is known as field flux control. The third type of control is field flux control. It can be field flux control or field current control, because flux is controlled by having the current of the field circuit controlled, right? So, again looking at this equation, we can say we can modify the flux, but keep VA and RA as constants. I am not going to change both of them. So, I would say VA is at its rated value and RA is inherent armature resistance. So, if I have no modification in the armature resistance and no modification in the applied voltage, very clearly this tells me that when I increase the flux, which I cannot do much because I have already been close to saturation point. The only thing what probably I can do is to reduce the flux, because I can include additional resistance in the field circuit and I would be able to deplete the flux if I want to. So originally maybe I had, a flux of 0.1, 0.2 Weber. Now maybe I would try to bring it out to 0.05, 0.06 Weber. So I would be able to reduce the flux by reducing the field current by including additional value of field circuit resistance. So I would be able to reduce IF, reduce flux by including RF external. So I am going to include a field circuit resistance externally. So what is going to happen in this particular case is, let's say I have the original speed torque characteristic somewhat like this. This is my speed, this is my torque, this is the inherent speed torque characteristic. What I mean by inherent is I have not intervened with any of the parameters. RA is original value, RF is whatever is the original value, I have not included anything extra. What I am including as the armature voltage is rated value. I have not increased or decreased any of them. All of them are at nominal values, whatever is the normal values. So this is originally what I got as VA by K5. Speed is 0, torque is 0, so this is the no load speed of the machine, VA by K5. Now I am trying to reduce actually the excitation. Very clearly, when IF is decreased, omega naught will go up. Right? Do you get this point? Because omega naught, or the no load speed, is going to be VA divided by K phi, and phi decreases. Right? Because of which I am going to have definitely reduction in the flux will cause an increase in the speed. If you actually look at the motor mechanism, you can say if I reduce the flux at a given speed, and my VA is also a constant, the back EMF will drop, because back EMF is proportional to flux multiplied by speed. The speed had been the same value. It is governed by the mechanical time constant or inertia. So it will take a while before it changes. The speed will remain the same. I have reduced the flux. When I reduce the flux, the back EMF is going to drop. When the back EMF drops, immediately I would see that the armature current rises in a transient manner. Once the armature current rises, I will probably generate a larger torque. If I generate a larger torque, there will be an acceleration. So the speed automatically increases. If the speed increases, originally I had K omega phi. Phi had decreased. Now the speed will hit that value such that K phi omega comes back to its original condition. So invariably, when you reduce the flux, you will see a transient increase in the current, which will eventually settle down at the original value itself. But in the process, if IA settles down to the original value, the torque has to drop, because torque is K phi IA. Right?